All right, so for our second talk this afternoon, we have Guido Bosco, and he's going to tell us about Hodge theory for p-adic analytic varieties.
Thanks a lot for the introduction, for the invitation to speak here. So my field of interest is p-adic geometry, and today the story I want to talk about is about Hodge theory of p-adic spaces. But maybe let me start from history, which is probably more well known, namely from complex Hodge theory. Let me begin with the following classical theorem, the Rham. So given X a compact complex manifold, then the rational singular cohomology of X base range to C is isomorphic to the Rham cohomology of X. So here the Rham cohomology is defined as the hypercohomology of the complex of holomorphic differential products. So this theorem is quite cool because it says that there is close relationship between the topology and the complex geometry of X. In fact, the singular cohomology of X is defined in terms of the topology of X. Instead, the Rham cohomology is defined in terms of the complex structure of X. But from this theorem, for example, one can deduce that the Rham cohomology is a topological invariant, and on the other hand, using the fact that the Rham cohomology is easier to compute, one can for example, compute the Betti numbers of X, so the number of n-dimensional holes in it. So today I want to explain you a p-adic analog of this. And so let me fix a prime number P, and let me denote by QP the field of p-adic numbers. So I have to first tell you what's the p-adic analog of a complex manifold. So let me start remarking that if one trivially copies the definition of a complex manifold, replacing C with QP, one gets spaces which are totally disconnected, since QP is totally disconnected. So since these objects are useful in certain contexts, but they do not have a very interesting geometric structure. So in the early 60s, John Tate found a way somehow to rigidify the situation, define the correct analog of a complex manifold in the p-adic setting, which he called rigid analytic varieties, that for simplicity I will just name rigid spaces. And for example, in this setting, one can make sense of the fact that the closed unit disk is connected as it should be. Later on, there were other approaches to p-adic geometry, mainly by Rham, Berkovich, and Cooper. So the goal for today is to explain you some recent advances in the Hodge theory of p-adic rigid spaces. So let me start by remarking that for smooth rigid spaces of a QP, then there is a well-defined Rham cohomology theory. So now I have to tell you what's the analog of singular cohomology in this context. And the answer is that is the cohomology for rigid spaces, which was developed by Berkovich and Uber and several other people. And of course, I have to say that in the case of algebraic varieties, the étale cohomology was defined by Grothendieck and studied by its school. So let me fix the notation. So I will denote by QP bar a fixed algebraic closure of QP, and I will denote by C the completion QP bar, and this is this called the field of complex p-adic numbers, and one can show that it is algebraically closed. And I will denote by GQP the absolute Galois group of QP. And given a rigid space X or a QP, I will denote by XC the base change of X to C, and attached to such a space we have the rational exact cohomology on which the Galois group of QP acts. So this will play an analogous role to the singular cohomology for complex manifolds. So the analog of the Rham comparison theorem in this context was proven by Schulze. So given X a proper smooth rigid space over QP, so here the properness assumptions should be thought as the analog of the compactness assumption for complex manifolds. So it showed that the rational étale cohomology groups are finite dimensional QP vector spaces. And base changing the rational étale cohomology to be the Rham, we get an natural isomorphism with the Rham cohomology base change to be the Rham. And such isomorphism is equivalent for the action of GQ. So here Rham is the famous field of Fontaine of period. So in first approximation, you can think of it as the Laurent series over C in one variable, but the isomorphism that I wrote is not equivalent for the Galois action, and moreover, Rham has a natural topology which is not compatible with the one on the Laurent series. So of course, this theorem was in the case of algebraic varieties was conjectured by Fontaine and proven by the work of many people, including Fontaine, Messing, Falting, Zhuji, and later on by Bellinson and Nizil. So one difference from the complex case is that complex manifolds are locally contrastable, and this is not the case in the p-adic setting. So the idea of Scholze was the following: so introduce a finite a topology which is finite the étale topology that we call pro-étale, and for x as in the theorem, the étale cohomology is isomorphic to the cohomology computed in this pro-étale topology, so isomorphic to the pro-étale cohomology, and zooming in this pro-étale topologies show that rigid spaces are perfectoid spaces. So in other words, perfectoid spaces form a basis for the pro-étale topology. And using this fact, so the spaces are still not locally contractible, but using this fact, for example, to prove the finite dimensionality of the étale cohomology, he was able to adapt the argument of Cartan and Serre to prove the finite dimensionality of the Quine cohomology of compact complex manifolds. So this theorem is quite cool as the theorem for compact complex manifolds. In fact, for x as in the theorem, one can recover the Rham cohomology in terms of the pro-étale cohomology, simply taking Galois invariants in the Rham comparison theorem, using the fact that the action of the Galois group on the Rham cohomology is trivial. So one natural question is, conversely, can one recover the pro-étale cohomology, rational pro-étale cohomology from the Rham data? And the first positive answer in this direction was given by Nizil and independently by Barmore, Scholze, and Cesnavicius-Koshi-Kawa. So, so given X rigid space over QP, assume that X has a proper p-adic formal scheme frac X over ZP. So this means that that base changing frac X from ZP to QP, I get this. The rigid space X somehow has an extension from QP to ZP. And assume that this formal model is semi-stable. Roughly, this means that the special fiber, so the locus in which P is equal to 0 in frac X, has singularities which are mild. So it has normal crossing singularities. Here's a picture. So on the right, we have our rigid space X or QP, which are depicted as some kind of manifold. And it is the generic fiber frac X, and the special fiber is frac X leaving over FP as singularities which are mild. So in this case, one can recover the p-adic pro-étale cohomology from the following data from the Rham cohomology group, and together with another filtration, which is called Yod filtration, and a so-called Yodokato cohomology. So this is a cohomology theory attached to the special fiber of frac X, and comes equipped with the Frobenius action coming from the fact that this special fiber lives in characteristic P, and with the monogamy action, and which comes from the singularities of the special fiber. So you should think as this Yodokato cohomology as a refinement of the Rham cohomology. In fact, as simply as QP vector spaces in this particular case of the theorem, we have an isomorphism between the Guido-Bosco homology and the Rham as QP vector spaces. So in this particular case of the theorem, the Postdoctoral homology can be expressed in terms of the Rham data. And the proof of Barmore-Schultz and the group reduction case then extended by Koshikawa and the semi-stable case was to define a homology theory for p-adic formal schemes that, under the assumption this theorem specializes to the Postdoctoral homology, Rham homology, and Guido-Bosco one, and somehow enables to compare all these homology theories. So a natural question now is that, can one extend this theorem to any rigid space over QP without assuming any properness or without assuming the existence of a semi-stable formal model? But before trying to answer this question, maybe let me give you some examples of non-proper rigid spaces. So, of course, already the building blocks of rigid spaces, which are called affinoid spaces, are non-proper. But maybe let me give you a more interesting example. So an example of non-proper rigid space is the Dreamfield F-plane. This is the p-adic analog of the Poincare F-plane, and this is non-proper. And more generally, in the p-adic Langlands program, one is interested in studying the absolute Galois group of QP by studying its action on the p-adic Italco homology of generalizations of the Dreamfield F-plane, which these are called local Shimura varieties. And in general, they are non-proper, and in general do not have the same stable formal mode. So there are several issues to overcome. So the first issue is that in the non-proper case, the Rham et al. And so on homology groups of non-proper rigid spaces is infinite dimensional. And so in particular, it becomes important to keep track of the natural topology that such homology group carry, but this causes several issues to the fact that it's hard to do homological algebra when the object attends carry a topological structure. So despite these issues, we have the following comparison theorem, which was proven by Colmez, Tosquin, and later by a different method by myself, and slight more generality. So given X a rigid space over QP, the Postdoctoral homology, rational p-adic Postdoctoral homology, can be recovered from the following data. So again, as before, we have the Rham homology of X plus an filtration, and I put smooth between parentheses because I feel suitably interpret what's the Rham homology in this case. This theorem also holds true for non-smooth spaces. And from a certain homology theory called the Guido-Bosco homology, which is attached to the base range of X to C. This again comes with the Frobenius and the monogamy action. And it is defined locally as the Guido-Bosco homology of a semi-stable formal model, as in the previous slide. So yeah, I mean, basically using the fact that the in a topology, smooth rigid spaces are have a semi-stable formal model. So zooming in this topology, we have such a semi-stable formal model, so we can apply the Guido-Bosco homology of the special file. So apart from this technicalities, what you get from this is that the rational p-adic Postdoctoral homology can be recovered from the Rham data, which is usually easier to compute. But for example, using this theorem, one can explicitly compute the p-adic Postdoctoral homology of the Dreamfield plane that I mentioned before. Or one can prove new vanishing results for the p-adic Postdoctoral homology of Stein spaces, which are the p-adic analog of the Stein spaces of in complex geometry. So let me just briefly say a few words about the proof that I gave in my thesis. So the proof uses a globally defined homology theory for rigid spaces, which somehow interpolates between all these homology theories. So between Poincare, Guido-Bosco, and the Rham homology. And I find it useful to use condensed math developed by Klaus and Schultz to deal with the topological issues that I mentioned before. So this condensed math is a new way of doing algebra when the object at hand carry a topological structure. So let me conclude by saying some work in progress. So it might have seemed to you that this Yodokato cohomology that I mentioned before is a bit strange. It's a bit mysterious. And I think indeed it is. And in fact, one of the questions I'm thinking about is to find a definition of this Yodokato cohomology for rigid spaces without using any log geometry on resolution of singularities, which was previously implicitly used. So I want to global definition of this Yodokato cohomology, which also extends to coefficients. And in particular, I'm trying to, if I'm entirely attached to rigid spaces, a stack such that green cohomology of the stack computes this Yodokato cohomology theory. So, thanks.
Questions?
Rigid space, do you use the definition of Berkovich definition?
I mean, I use like the definition, but
Because I have the feeling that Berkovich is some kind of over-convergent version of that, and that this was important for
yeah, I use the
Heisenberg.
definition, but somehow also implicitly regard all my rigid spaces as a p-adic spaces in the sense of Uber.
And another question, in this non-proper case, what do you call the Hodge filtration?
I call the Hodge filtration in the derived sense. So for
Just using the spectral sequence.
no, like so I'll give you an X. Let's say QP is in free space. So the Hodge filtration is actually defined on the derived Rham cohomology of X as the homology of X of the this complex here.
But you need the derived thing. And
Yeah. But I was told that I was not supposed to speak about derived stuff, so yeah, that's why I put H asterisk.
Sorry, why do you need the derived thing here?
Yeah, this theorem is like implicitly somehow it's in derived sense, like everything's derived. So the derived Poisson cohomology can be recorded from the.
Sorry, spectral sequence doesn't necessarily generate, right? So the filtration is in the sense of context.
Sorry, but like it's a finite filtration in the smooth case.
Yeah, but
But it's not filtration on cohomology groups.
Yeah, no, I understand.
Yeah.
It's a filtered object, yeah.
about the topological problem of, because it's infinite dimensional, are things easier in homology rather than cohomology?
I don't think so. Yeah.
I was thinking to topology.
Yeah, but you using this condensed math of Clausen-Schulze, actually one can do homological algebra also when the object at n carry a topological structure somehow.
What is your globally defined cohomology theory defined in?
It's called symptomic Farfans and cohomology, so quite fancy. I can explain to you later.
So, do you have a similar formula to recover the Etoile cohomology, just like a classical case? So you take a filtration and the Rham use invariant.
Yeah. And I mean, this actually is this basically this term says that there is a pullback diagram relating the derived Poisson cohomology in terms of the Rham cohomology.
It's a very similar formula.
Yeah.
Do you need to work over a finite extension of QP or?
Yeah, John, I can also take a discrete value extension on QP with perfect residual field.
But not like CP?
Hmm?
You don't have results for.
No, but
CP? No.
I mean for X over C.
Oh, yeah.
Yeah, but then I have to replace this Rham cohomology with the Rham plus cohomology.
Okay. But then it's okay.
Yes.
Thank you.